Now that we're done with our little hubs and repeaters history lessons, some good material for your exam there, of course. But the next step forward was the step to bridges. And it was a giant step forward for one reason that you're about to see on your screen right now, because the introduction of bridges meant that we could create smaller collision domains, which in turn resulted in fewer overall collisions, which for reasons we discussed previously was fantastic. Now, bridges didn't necessarily replace hubs and repeaters. What you ended up doing was using the bridge to segment your network. It actually go between your hubs, like in this particular drawing. And here we have two collision domains. And again, if the terms collision domain and broadcast domain are new to you, it may sound wrong that having more collision domains is a good thing. But actually, the more collision domains we have, the fewer overall collisions we end up having. So that was a big step forward. We're logically segmenting the network with a bridge. The chance of collisions is lessened. So that was definitely a step forward from having the old shared media. Bridges don't help, though, with lessening the number of broadcasts on our network. When any host on this network sends a broadcast, every other host on that network is going to get a copy of it. And that's actually what we're trying to avoid. And let's go ahead and bring up that next screen. Here we go. Because bridges, as far as the broadcast goes, it still results in one large broadcast domain. And that was it. Let me bring the previous drawing up for a little comparison here. Our collision domains, that's what we get with a bridge. We get multiple collision domains. But with a broadcast domain, we've still got one giant broadcast domain. So obviously a huge step up here, right, from hubs and repeaters. But we need some more help with collisions, because having smaller collision domains is good, but we can always get better. And we could use any help we can get with broadcasts. So we got all of that and more really with the introduction of switches. And here we've replaced the hubs and repeaters and bridges, bridge in our network with a single switch. This is the universal representation of a switch, by the way. You could walk in tomorrow, look at a network map, and if you see these boxes with 4 arrows on it pointing two each way, left and right I should say, this is a switch. And you're expected to know that on your exam. So the switch behaviors we talk about, they could show you a diagram like this and just say, what happens if X? And they're not going to say, hey, this is a switch. They expect you to know that. And here's that the full rogues gallery, if you will. Here's your hub with your single double-headed arrow on top. There's your bridge, and there's your switch. Now, the great part, one of the best parts about the switch, by connecting each host to a separate switch port, we create a collision domain for each host. Each switch port is its own collision domain. Collisions literally cannot occur. So where we had one collision domain with a hub or repeater, and we could segment the network somewhat with a bridge, we now have 4 separate collision domains in this particular diagram by using a switch. And even better, to go along with that, in addition to eliminating the collisions, each host is going to have far more bandwidth available. Because when hosts are connected to individual switch ports, they don't have to share anymore. And that's actually a situation where not sharing is a good thing, because with the correct switch config and the network cards, each host can theoretically run at 200 meg, 100 meg sending and 100 meg receiving. Now, Cisco switch default settings are great in so many cases, and I know networks, smaller networks, I grant you, where they've gotten a new Cisco switch, taken it out of the box, put it in, and they hardly do anything to it because it works that well. But one thing that Cisco switches don't do by default is break up broadcast domains. Now, we know that each host connected to that switch is in its own little collision domain, but unfortunately, they're all in one big broadcast domain, and we know what that means by this point. Certainly lots of unnecessary broadcasts. This is one default setting that you're very likely to want to change, and we're going to see how to do that while we talk about switching and do some labs. Before we move forward, though, let's review those key concepts. With hubs, we have one big collision domain consisting of all connected hosts. And with switches, each individual switch port is its own little collision domain. Hubs are only going to allow one device to transmit at a time, and there we have the shared bandwidth, where switches allow hosts to transmit simultaneously, which is a very good thing. When one host connected to a hub sends a broadcast. We know the deal here. Every other host on the hub gets that broadcast, and we have no way around it. Now, switches have that same behavior by default, but we can do something about it, and we're going to do that with virtual LANs in this part of the course. A term I want to introduce you to here, you see it every once in a while. Microsegmentation sounds really complex. It's not. It's simply a term that's used in Cisco documentation to describe the one host, one collision domain segmentation that's performed by switches. That's really it. I see it pop up in Cisco documentation and in their books every once in a while, so it's a good term to know for a Cisco exam. Now let's talk about the frame forwarding decision-making process. And again, nothing real complex here, because a Cisco switch can really do one of three things with an incoming frame. That switch can forward the frame, it can filter it, or it can flood it. And you're going to see here that the entire decision-making process, it actually is pretty simple. It could be worth big points on your exam too. And we're going to go through a diagram, actually, not a real-world network. I'll probably mention that a couple times because there's one particular, one of those choices I want to illustrate to you. And there's one little oddity that I want to introduce you to, and you're going to get tired of hearing me say this. I'm just warning you ahead of time, but you will thank me after you're a CCENT and a CCNA. Because when a frame enters a switch, which one of the following does the switch look at first? So you know this is a trick question, right? just from the tone of my voice. A, the source MAC address, or B, the destination MAC address. I don't have the entire screen in front of you yet, but those are your only choices. And if this is new to you, if you haven't seen it before, you would think the same thing that I thought. Well, the destination MAC. Why do we care about where a frame came from? What does it matter to the switch? We're trying to get it to the destination, right? So you know with that explanation, the correct answer has to be A. And actually it is. And again, it would make perfect sense if you thought that. If you thought, hey, it's going to look at the destination MAC, it doesn't care about the source MAC address. Well, the switch wants to get that frame to the right destination, and what better way to do that than look at the destination address? And it'll do that after it looks at the source MAC address of the incoming frame. And the logical question you're thinking right now is, Chris, why does the switch care? Why does the switch care where the frame came from? And the answer to that is because source addresses are how the switch builds and maintains its dynamic MAC address table. Because the switch has to have a table, it's got to have some kind of lookup to look at a destination of a frame and say, okay, here's the port we want to send this out. And the way that it builds that MAC address table is by looking at the source MAC address of incoming frames. Now, this is not quite the only reason that the switch looks at that source MAC first. There are others, and you'll see in this section when we're doing some laps what's going on there. But it is, I would say, the major reason. And there's one big reason for that. When we're working with dynamic routing protocols later in the course, you're going to see that we've got several dynamic routing protocols to work with. These are routing protocols, RIP, EIGRP, OSPF. They run at layer 3, and they're going to be used to build a routing table. But we have to have a switching table as well. And while we do have protocols at the switching level, like say the spanning tree protocol, which we'll be working with here, that is not a protocol that builds a switching table. That's actually to prevent switching loops. So we really don't have, RIP for switches or OSPF for switches. There's no way to dynamically go out and discover all the MAC addresses. So what happens instead is the switch builds its MAC address table by looking at the source of an incoming frame and saying, okay, I'm going to make an entry for this one off this port. And you'll see what I'm saying here in a moment. I've got an illustration here for you on the board. Now, we could build a MAC address table with static entries. We could also build a routing table with only static entries. This is not a particularly good idea. This approach has serious drawbacks. First off, every time you add a host to the switch, you'd have to remember, okay, I got to go to the switch, I got to make a static MAC address entry for the host, and it's easy to forget that. It's really easy to mistype a MAC address. I mean, you're dealing with a lot of letters and a lot of dashes there, etc. You don't want to do that. It's not efficient. It's just not an efficient way of doing things. It's not lazy to let the switch do the work in this case. It's smart. Also, if a port goes down, and you switch the host connected to the bad port to a good port, I mean, that's the first thing you want to do, right? You know, you've got somebody and you can see the switch port's gone bad and somebody says they can't get on the network, and I guarantee you it's always a vice president of something who can't get on the network. It's always someone very important, and, or at least thinks they're very important, and, you know, you just want to get them on the network. And you'll fix the problem in a second, but you know the first thing you want to do is get the user up and running, and then your phone's not ringing and they're not leaning over your shoulder, and you can fix the actual issue. Now, you're not going to have full connectivity until you add a new static entry for that host's MAC address if you're using static entries. And again, it's easy in the heat of battle to forget to remove the old one or to mistype it. So again, if I have a choice, and I do, and you have the same choice, between letting the hardware do the work and me doing the work, I'm going to let the hardware do it every time. It's much more effective to let the hardware carry out dynamic operations than you and I as the network admins handling everything statically, because frankly, we have enough to do. Okay, now we're going to take a look at how a switch builds that all-important table. And at the same time, we're going to see each of those frame forwarding options in action. We're going to start with 4 hosts and 1 switch, and we are going to do this one on the board because the MAC addresses are a little odd here. I want you to see it on the board, and then we'll do plenty of live labs later in the section. Now, when I bring this diagram up, notice that hosts A and B are connected to a hub, which in turn is connected to a switch. I've used another representation of the hub. It won't hurt you to see that either. For clarity's sake, instead of take, we'll have each host use its letter 12 times to make up its MAC address. And this is what we're going to use right here. We've got host A with the all A's MAC address, host B with the all B's MAC address, host C with the all C's MAC address, and we all know what host D has. Hosts A and B are connected to a hub, which in turn is connected to our switch port FAST01. I'll just call it port 1 on the switch. Host C is connected to port 2. Host D is connected to port 3. Again, this is not a real-world scenario. I pride myself on bringing you plenty of those, and we will do them, but I want you to see this one because there's one of those choices that's only made under certain situations, so we have to go a little outside the box here. Now, we're also going to assume that the switch has just been added to the network, and that brings up another important point. When you first power a switch on, you will see some entries in the MAC table, but they're going to be for the CPU, and that's it. And it's going to look something like this. I'll show you this on the board now, and we'll be seeing it on live equipment later. But show MAC address table. One quick discussion or note about this command. Sometimes with some iOS versions, you have to put a dash between MAC and address. Some of you veterans out there are saying, hey, what happened to that dash? It's not a big deal for your exam, but the newer iOSs, the latest and the greatest, which you do not necessarily have to have for practicing these commands, that's the only command I saw that was really different, is that one little dash is missing. I have no idea why they finally decided to remove it, but there you go. So you're going to see some entries in there, but you'll notice that they are static entries, and when we have dynamic entries added via the reading of the source MAC address of incoming frames, they're going to be listed as dynamic. And the only way now that the switch knows where the hosts are is for you and I to add a bunch of static entries, which is very bad, or let the switch learn the address dynamically, which is a great idea. And on the very next video, we're going to go through the steps of how the switch would learn where all 4 of these devices are, and we will see all 3 of the frame forwarding decision choices in action. So for your exam and the real world, you'll know exactly what action a switch is going to take and why, because you got to know why. See you on the next video. We'll jump right into that.